Start with method 2. Let's look back. What are the numbers? 126 and 144. So if I write out 126 and 144, what we have is 126. Can we divide it by 2? Yes. We get 63. Can we divide that by 3? Yes, adds up to 9. 21. 21 divides by 3. 7 divides by 7. So 126 is equal to 2 times 3 times 3 times 7. And 144, you can divide that by 2, you get 72. Divided by 2 again, you get 36. Divide by 2 again, you get 18. Divide by 2 again, you get 9. Divide by 3, you get 3. Divide by 3, and we get 1. So 144 is 2 times 2 times 2 times 2 times 3 times 3. Now, to find the greatest common factor, it has to be something that divides both of them. Can you see that 2 divides both of them? But only one 2 can divide both of them, because you can't divide 126 by 2 2s. For 3's, they both can get divided by 3. In fact, they both can get divided by 2 3's. Those are the only factors they have in common. So our greatest common factor will be 2 times 3 times 3, which is 18. That's the largest number that divides both of them. Now, this provides us with a technique that if we do the prime factorization of both numbers, we can find the greatest common factor quickly. With smaller numbers, this isn't the fastest technique, because smaller numbers, if I told you 35 and 20, you would say, well, the biggest number that divides both of those is 5, and you could just see it right away. But with bigger numbers like this, this does provide a nice method to figure it out. The old method, what you would have done is just use your division facts, and we'll start with 126. That's equal to 1 times 126. Does it divide by 2? Yes. It's 2 times 63. Does it divide by 3? It's 3 times 42. Does it divide by 4? No. Does it divide by 5? 6? Yes. 6 by 21. Does it divide by 7? 7 by 18. Does it divide by 8? No. Does it divide by 9? Yes. It is 9 times 14. Does it divide by 10? Divide by 11? Does it divide by 12? Does it divide by 13? And once we get to 13, we can stop, because the 14 is already on the other side. So we would only have to go up to 14. Now we know we've hit them all. You can see this is not too fast. When you go to 144, yes, feel really good about that. 1 times 144. 2 times 72. Does it divide by 3? Yes. 3 by 48. Does it divide by 4? 4 by 36. Does it divide by 5? No. Does it divide by 6? Yes. 6 by 24. Does it divide by 7? No. Does it divide by 8? Yes. 8 by 18. Does it divide by 9? Yes. 9 times 16. Does it divide by 10? No. 11? No. 12? Yes. And now you would know you're done, because it's 12 by 12 and it sort of hits the numbers the other way. So now that you've created this big list of each of them, you look for the ones in common. Ooh, they both can be divided by 1. That's not the biggest one, though. They both can be divided by 2. They both can be divided by 3. They both can be divided by 6, not 7. They both can be divided by 9. Coming around the other side, 18. 18 is the biggest one. Yes?
Are we supposed to know how to do both methods? Like
You can pick which method. You don't need both methods. I don't. For bigger numbers, this isn't very efficient, is it? And could it be easy to miss one? To say, I don't think it divides by 7. And if you miss 7 times 18, you're going to miss the greatest common factor. Whereas the other technique allows us to say, okay, when we write the prime factorization, which ones are in common? And if we see which ones are in common and circle them and multiply them together, we get the greatest common factor.